Well, good morning, everyone. It's really wonderful to see you. Actually, what was really wonderful for me was to hear you, because I walked in from outside the door over to the right side, and I just heard this roar of energy in here, and that energized me. So anyway, I'm delighted to see you here. Just a little bit about me. I spent my early career as a hydrogeologist. I worked on geothermal energy, and then I worked on nuclear waste disposal, and then I worked on sort of groundwater contamination kind of problems associated with agriculture and industrial processing and so forth. And in 1998, I was the director then of the Earth Sciences Division at Lawrence Berkeley National Laboratory. And my job was to sort of figure out what should we be doing next. And I thought the most important thing that we could possibly be working on is the climate and energy problem. The challenge to meet the growing needs for world energy, maybe twice as much sort of by the end of the century as compared today. But at the same time, we had to deal with the environmental issues, the geopolitical issues associated with our energy system. So since 1998, that's what I've done. A good deal of my research works on one particular technology called carbon dioxide capture and storage, though I do other things as well. Particularly sort of energy systems analysis, looking at things like net energy of renewable energy systems and net energy of storage systems. So enough about me, and we'll get on with the program. So first of all, thinking about energy. I mean, energy is interwoven into every part of our life that we can think about. They're the obvious things. When you think about energy, you probably think about going to a gas station and filling up your car, but in reality, it's interwoven into the physical infrastructure, the embodied energy of buildings, lighting, water, agriculture, all the electronic gadgets we use, and I would dare to say that one really can't imagine life without access to modern energy if you're sitting here at Stanford University today. And what makes energy so interesting and important and challenging is that our ability to meet the needs for human energy is intricately interwoven into many other global challenges that we face. Protecting the environment, meeting basic human needs for food, water, shelter, and energy. Energy is the economic engine. If we don't have access to affordable energy, it's very difficult to sustain the kind of economic growth that's led to a betterment of people's lives. And finally, there are many aspects related to national security. And interestingly, more than ever, I think we're starting to see these play out with some of the tensions in Europe and in the Middle East. So just to delve into these a little bit more, to highlight some of the most challenging issues. The first is an issue, of course, you all know about, that when we burn fossil fuels, carbon dioxide is emitted into the atmosphere. It gradually builds up in the atmosphere, and here's a graph, a very, very famous data set collected by Charles David Keeling beginning in 1958, where he began to measure the carbon dioxide concentration at the top of a volcano in Hawaii, far from any land sources. And what he began to notice almost immediately is a sort of inexorable rise in carbon dioxide concentrations. And now carbon dioxide concentrations exceed 400 parts per million compared to about 280 before the Industrial Revolution began. And the question then is, well, what are the consequences? Well, in fact, there are many signs of climate change all around us, from the obvious ones like the temperature of the atmosphere is increasing, but also ones that are not so obvious, like increasing intensity of or increasing frequency of extreme weather events, such as floods and droughts and so forth. The shifting of habitats of animal species. These are now well documented and well attributed to anthropogenic emissions of carbon dioxide. So here in California and the United States, this often tends to be the largest focus of our environmental concerns about energy. But in fact, if you're living in many parts of the developing world, a much more pressing and urgent problem has to do with air pollution. inappropriate or inefficient burning of fossil fuel leads to the creation of a lot of soot, which then creates terrible, terrible local air pollution problems that are damaging people's healths. And here's just an example. This is on the streets of Pakistan, people riding along the street on little motorcycles, and basically they're choking from the terrible quality air. And I've spent quite a bit of time there, and often you'll go out of your apartment or your house in the morning, and you literally wonder, where's the forest fire? You know, because the intensity of smoke in the atmosphere is so huge, which brings up another point, that much of the pollution in this part of the world is associated with burning of biomass, agricultural waste, wood products, or animal dung for both heating and for cooking. And this leads to lots of local pollution. So if we think about the world, here's a map, and it's color-coded by those areas which have the largest reliance on what we call traditional biomass for cooking fuels. And you can see large parts of sub-Saharan Africa and Asia. The majority of people today are still relying on these heavily polluting fuels. In addition, the sheer amount of time that it takes to go collect these materials, gather them, significantly deter from, for example, childhood education, because it just takes a lot of time to do this. And there are terrible health quality problems for families. Often the biomass burning is done indoors with no ventilation, and so women and children in particular are exposed to very high amounts of smoke, which has all kinds of challenges for eyesight, for example. Thinking then about electricity, here's a map showing those who lack access to electricity. There are about 1.5 billion people out of our 7 billion people on this planet. 1.5 billion have no access to electricity. Again, you can see sort of the hot spots of deficit are in sub-Saharan Africa and South Asia as well. And I think this map, though, really belies a much bigger challenge, because you go to those parts of the world that are indicated to have electricity today, and in fact, the electricity reliability is so spotty that maybe you're getting electricity several hours a day, and maybe not. So the need for more electricity in many parts of the world is crucial to the health and economic well-being of these communities. So there are more challenges as well. If we think about oil, this is a graph. It shows the price of oil. If you look at the light green curve, that's oil in present-day prices, and you can see that initially it was extremely high when it was such a novelty to get oil out of the ground. It then dropped to low values and actually remained low for many, many decades. But beginning in the 1970s, we began to see the first of the oil price price shocks, and you can see very quickly like a 3- to 4-fold increase in the price of oil. Imagine if you're heavily reliant on this as the engine of your economy, and all of a sudden you're having to pay 3 to 4 times more. It's very devastating, and in fact it's been shown that many economic downturns are associated with these periods of instability in the oil price. And if you look up to the present time, we can see that we're near record highs in our oil prices. A new dimension to energy, at least new in the context of sort of modern thinking, is that now energy is actually being used as a weapon. If you have a country that is heavily reliant on another country for oil or gas, in this case we're thinking about the Ukraine, simply refusing to send those deliveries can basically make it so that the country has few options in order to protect its own political interest. If we look at Europe, which is heavily reliant on Russia today for gas, they've been very loath to take a strong political stand associated with the recent tensions between the Ukraine and Russia. So energy as a weapon is on the horizon. So I've said a lot of challenging things, sort of the motivation, the bad reasons why we need to really focus all of our energy on and attention on this important subject. But at the same time, there is so much exciting and so much good going on in energy. The energy system is in a tremendous state of flux. And if you think about the energy system, you sort of need to think about a giant, ocean-going liner that, it's very big, it's very, very slow to turn, it's very slow to stop, it's very slow to start, so changes in the energy system, this huge system that sort of is about 10% of the global economy, are typically really slow. But what we've seen recently through all kinds of technological innovation is that all of a sudden the energy system or components of it almost feel like a startup. And I'd like to highlight these both in terms of sort of some of the good news about growing global demand for energy. I'll talk a little bit about shifting resources. Until now, we've been heavily reliant on oil, gas, coal. About 85% of our energy system, and we're starting to see some shifts there. I'll talk about new business opportunities associated with innovation, much of which is coming right out of Silicon Valley, and then also bring up some national security dimensions to changes in the energy system that are very important as well. So looking first at the global energy demand, here's a graph looking at about 30 years of energy demand, and the first and most important thing that you see is sustained growth in the demand for energy. Well, one can look at this in a negative way, but you can also look at this as a very positive way, is that all of this demand growth is actually driven by providing energy for industry, for a growing middle class, for the most impoverished of people in Asia. So people are beginning to increase the access to energy that will allow them to establish a good quality of life for themselves. And it's likely that through 2100, we're going to continue to grow our energy system, perhaps to be 50% greater than it is today, perhaps to be 100%. And a lot of that will depend on how clever we can be to design new and more efficient ways of converting energy to useful energy services. And I would imagine that some of you, and perhaps even many of you, one way or another will get involved in making energy use more efficient so that we can constrain the global energy demand while at the same time continuing to meet the growing need for energy services. So that's some good news. The second thing is, if you look back 5 years ago and somebody said that photovoltaics were going to be growing at a rate of 40% per year, and not just for 1 year, but that it was going to be sustained over decades, if somebody told you that the price of photovoltaics was going to drop by about a factor of 4-fold in about 5 years, everyone would have said, no way. The mythology was photovoltaics are simply too expensive to scale. And in reality, photovoltaics have been increasing at 40% year over year for the past decade, and these trends continue as we go on. In large part, this is due to the scale-up of manufacturing in China. However, there are also very, very exciting technical innovations that are taking place. This is a very famous chart prepared by the National Renewable Energy Lab, and it documents all the different types of photovoltaic devices that there are, and it documents their efficiency and how their efficiency changes over time. And if you look at the last 5 years or so, all of a sudden, things that were sort of not increasing very fast, well, all of a sudden a good increase. Similarly here, organic photovoltaics. And then on top of that, there have been some total surprises, like this little thing here. Notice that this dot, this is a completely new material for photovoltaics. It's called perovskite. And in this short time, you see increases in efficiency to now that these materials are almost efficient as things that have been under development for 20 or 30 years. So very, very exciting time. And again, I would imagine that many of you here will work to one degree or another associated with material science that can improve photovoltaic efficiency and the durability of those devices. So moving on to wind. Wind has been another very exciting story. If somebody told you that Iowa was going to have the largest fraction of its electricity from wind power a decade ago, people would say, no way. You know, they'd say maybe California, but Iowa. The reality is that with new wind turbine technology and the decreasing costs associated with wind, it's now actually quite profitable. And in some cases, wind energy is the lowest cost energy that you can actually provide. And as a consequence of this, worldwide, we have seen a growing scale up at about 30% year over year for more than a decade. And again, this trend is continuing. And there are some real innovations that are taking place associated with offshore wind, both with the turbine technology, the marine technology, as well as the idea of having large subsea cables which could gather that electricity and bring it to shore. It's a very exciting time. So other things. So the conventional wisdom associated with our fossil fuel resources was that we were basically running out of low-cost oil and gas. You know, that was, you hear peak oil, you know, it's just inevitably going to go downwards. But there was some real innovation, actually, which started in the 1980s and then eventually came to fruition in the mid-2000s, where people discovered that rocks that were formerly thought impossible to get oil or gas out of, in fact, you could get gas out of these rocks. And not only that, it turned out you could get oil too. So through the technology called hydraulic fracturing, or fracking is a more popular word to say, what has happened is that the amount of natural gas produced in the United States has increased by about 40% since about 2004. And all this is associated with this shale gas revolution. So again, who would have thought that we have an entirely new source of natural gas that could augment our supply? Now, you might be saying, well, is this a good thing or a bad thing from a climate point of view? Well, if you compare it to burning coal, it's significantly better. It has about half the CO2 emissions. It has far fewer particulate emissions, mercury emissions, radionuclide emissions. It doesn't create slag piles of ash that are left over after you burn the coal. So it can be very beneficial. On the other hand, there are researchers now discovering that our natural gas system is way leakier than we thought. In fact, the distribution systems in cities, that at major gas processing facilities, that there are actually big leaks. And if that happens, all the benefits could be negated because methane is a very, very powerful natural gas. So we have faculty members here who are leaders in the design of technology and implementation of these technologies for looking for leaks so that they can be shut off. So moving on, electric cars. You know, if you said to somebody that the Tesla Model S or an electric car was going to be the #1 selling car in Norway in 2014, everyone would have said, no way. You know, electric cars were thought of as sort of clunky things, that there were a bunch of electric trucks that were deployed about a decade ago, but they were actually pulled from service. And innovation in the Valley just defied conventional wisdom and said, we are going to make the most exciting cars, electric cars. And you know, here's a picture of the Model S. And they have a tremendous factory in Fremont. You're going to go visit that. You're going to meet J.B. Straubel, who was a Stanford student who always loved cars and loved electric cars. So he'll be here on Friday. You'll get to meet him and hear his personal story. And they've just announced that they're building a giant factory to produce lithium-ion batteries in Nevada. So again, who would have thought that the United States would be becoming a major industrial powerhouse of making batteries? We haven't done that. You know, that all moved over to Asia, and here we are. So much can change. Like I said, it's almost like energy feels like more like a startup industry rather than an ocean-going liner slowly turning around. And just another really interesting dimension is, an energy-independent North America. So Canada, Mexico, United States, energy independence. That was almost unheard of, again, a decade ago. You can see this top graph here. This is the import of oil, and if you look at this period here, just again, 5 years ago, we were importing about twice as much oil as we were producing in the United States. Well, what are we seeing? That the amount of oil that we're producing is going up, again, because of that technology of hydraulic fracturing, and the imports are commensurately coming down. And it's now forecasted that somewhere about 2025 that North America could actually be energy independent. So that's some of the things going on. So what you all and we together, the faculty and the students and the staff here, have the opportunity to do is to think about what sort of energy system do we want for this century. For me, I want it so that everybody in the world has access to energy that's affordable. From an economic point of view, I'd like energy that has low enough cost and is reliable enough so that we can support a thriving industry. We want an energy system that's secure from political manipulation so that it won't drive our foreign policy. And we want an energy system that's protective of the environment, so clean air, clean water, stable climate. And that brings me to the mission of the Precourt Institute for Energy. I'm the director of that institute. Any of you, I'd love to talk with you. If you have ideas about how we can be more helpful to you as students, ideas for projects, please bring them to us, because your ideas are often the very, very best ideas that we have. So we do 4 things in the Institute. We do game-changing energy research, all the way from energy policy to energy technology. We establish partnerships with national laboratories and industries to accelerate the deployment and scale-up of these technologies. We provide opportunities for educating future leaders, that's you. And also, very importantly, we need the whole world to understand the current energy context and the opportunities presented ahead. So we do a lot of work with educating the public broadly about energy. So at Stanford, there are over 200 faculty members who work in energy. And if you think about what makes a great research university, it takes, well, really 3 ingredients. 1 is a great faculty. 2 is great students, and that's you. And that's why we're all so excited to be here working with you. And a great staff to help us realize the programs that we try to carry out. So here's just a quick table showing the range of areas that we do research. So renewable energy, lots on that, especially PV and renewable fuels, very, very strong areas of emphasis. Fossil and nuclear energy, particularly fossil energy, advanced combustion, carbon capture and storage, end-use and end-use energy efficiency, lots of work on behavior and energy and transportation efficiency. Energy storage and transmission, lots of work about the electric grid of the future, and you're going to hear more about that from Arun Majumdar on Friday, and lots of work on batteries and other concepts for storing energy. Lots of work on environmental impacts, and Chris Field will be the next speaker, who was the head of Working Group 2. Actually, he just walked in. And then finally, lots on policy and economics. And in reality, solving global energy challenges take this entire constellation of people, which is why we have all of you here today. That we would like you to establish a robust set of friendships, relationships, ability to converse with each other, understand each other's language, so as you go on into your careers, that you are prepared with the full spectrum of knowledge needed to really have an impact. At Stanford, there are also a number of research centers of excellence. Over the time, you're going to hear more about these. There's SunCat, Bay Area Photovoltaic Consortium, on and on and on. Sometimes it's a little confusing. Sometimes I call it the alphabet soup of energy at Stanford. But we do have many centers that you can engage with as well. And those are listed here. And energy courses, we have over 400 energy courses. That's kind of daunting. And we have a very nice website indicated there, and you'll have these slides. And it's basically a searchable database that you can go look for the kind of classes that you're interested in taking. We also have a weekly energy seminar. We sometimes jokingly call it Energy Church. It's Monday at 4:15. A couple hundred people show up. Hopefully, if you come, you'll get to reconnect with each other. We often have social events afterwards, or we have poster shows and so forth. That is in the NVIDIA Conference Center, which is right in the middle of the Science and Engineering Quad. In the Huang building, if you go downstairs there's a nice auditorium. And we'll provide you more information about where to find these and so forth. And if you want to come the first Monday, we'll be having Diane Grunek, who will be talking about the EPA's new legislation. Oh, there's Diane right there. That has been promulgated so that it would reduce the CO2 emissions from our electricity sector by 30% by 2030. So anyway, it'll be a wonderful start. Also, many energy clubs on campus, student-driven activities. Strongly encourage you to participate in those. And then we have a number of symposia over the course of the year. The first big one coming up is for the Global Climate and Energy Project. It's really a technology showcase, but we also have some fantastic keynote speakers. We've got Chad Holliday, former CEO of DuPont and now chairman of the board of Bank of America. Dan Kamen, a world expert in energy for developing economies, and other very exciting people. And for women, we creating an environment where women are attracted to working in the energy area is very important to us. So we've had a series on breakfasts for women in sustainability and energy, so forth. So lots of those. And then finally, Stanford really puts its money where its mouth is. There's been a major overhaul of our entire energy system on campus that changed out our old CoGen, or is changing out our old CoGen plant with a steam and cold water circulating system with a completely new concept of a hot water and cold water loop, lots of photovoltaics that will result in reducing fuel use by about 30%, reduce CO2 emissions by 50%, significant reduction in water use. And also, the good news is it will actually save money. And so there is a picture of this facility in a couple of months. Actually, maybe it's next April. It will be available for public tours. Go check it out. It's really fantastic. I was there the other day. So now, just to wrap up, welcome to Stanford. I'm so thrilled you're here. I look forward to meeting all of you and talking with you over the time that you have here at Stanford. And thank you for participating, and I look forward to a great week. Okay, we have some time for questions. Don't everybody raise your hand at once. Okay, yeah, back there with the pink sweater, and then we'll come right in front of you. Yeah, you. Mm-hmm.
Will those slides from these presentations be posted anywhere?
Yep. Lee, where will they be posted?
On the conference website. Thank you. You're welcome.
Okay. And yes.
Thank you. That was really nice overview. So you mentioned that 50% or 100% by the end of the century increase energy. And I was wondering, first of all, what conditions that was and how annual are you talking about? And second of all, at what point do we have, is there a point that you imagine having enough energy? Or is that level off? Or is there...
Yeah. No, that's a great question. So it's really interesting. There's this conventional view that if you look at wealth, versus energy use, that there's some kind of linear relationship where it says the wealthier you are, the more energy you use. But actually, if you tease that data apart, in fact, what you find is that typically economies within a relatively short time get to some kind of value of the energy use per GDP, for example. And then they typically stay at that level for a long time so that they don't need to continue to grow. And actually, some places actually decouple the amount of energy that they use from their economic development. So I think it can stabilize. So your question about 2 times global energy, thanks for asking that. So what that assumes is that one day in the world we'll have 9 billion people, and those 9 billion people, any Italians in here? Okay, Italian. That everyone will use the same amount as the average Italian uses today. Okay? And the average Italian uses about between 25 and 30% of what Americans use today. So they're much more efficient. They are, an industrialized economy, so it's not like they're just a service economy. So that's that. So it does require that that some like the United States and Australia and those very energy intensive countries really ramp down. So we would need to cut our energy use by 2/3 per person in order to achieve those targets. Yeah, and who knows whether that's really right, but it's a place to start. Yeah, more questions? Yes?
I'm just wondering, in your opinion, what areas could the university use or areas of the energy game is Stanford perhaps a little underinvested or underrepresented?
Yeah, I think, in the technology areas, we have a fantastic program. There are places where we could improve that. So energy efficiency, sort of device level efficiency and systems level efficiency. I still think we have some improvements there. I think there's a big opportunity to further engage in the area of policy development. And that's why people like Diane Grunick were invited to join the university. She used to be a commissioner with the California Public Utilities Commission. And so more systematic engagement around that area, I think, is something that we can certainly do. I think that energy and ethics is another area. So we've done a little bit of work with the Center for Ethics and Society, but I would love to see more of the social sciences engagement on equity issues and so forth. So those are just some. Yes?
Is there anybody at Stanford or at Precourt who's interested in fusion?
There's nobody whose fusion energy is their major activity. However, at SLAC National Laboratory, which is why this constellation is so important, there are some people who have come from the National Ignition Facility, and now are staff members at SLAC, and I don't know how much they plan to continue their work in fusion. But yeah, you might want to say something about that.
Yeah, there's a Secret Cleanser who just arrived from Livermore, and he's been working on inertia confinement for quite a long amount of time. He's continued working to research methods and ways to improve on that. He's really looking at it from some fundamental difficulties of the mechanisms of confinement. So he just arrived 2 years ago.
Okay. Yeah, back to the question about what else could we do. We don't really have anybody working on nuclear technology. Bert Richter, who is also at SLAC National Accelerator Lab and a senior fellow, he's very interested in sort of nuclear energy policy, also incredibly knowledgeable about the technology, but we don't have anybody really actively doing research in that area. Okay, well, I think that it's time to move on. And I'll turn it back over to Tom.
Okay, let's thank Sarah.